Hi, I'm Jeff Yarger. I'm a professor of chemistry, biochemistry, and physics.
Hi, I'm Vladimiro Mujica. I'm a professor at the School of Molecular Science.
So we're using Atkins, second edition, Physical Chemistry for the Life Sciences in physical chemistry with a biological focus at Arizona State University. And we provide more information about the material for this course and all things related to kind of biophysical chemistry, at the following website. What we're making this video specifically to do is to take a few minutes and look at a specific discussion question at the end of chapter 3 in this textbook on phase equilibria. And the specific question looks at a figure 3.6, and it says, how would you expect the shape of this curve to change if the degree of cooperativity of denaturization of the protein were to increase or decrease for a constant value of the melting temperature? And so it's really asking a very specific question, but we want to take a few minutes here and kind of delve into some of the specifics. So I'll start by saying, the short answer is, as the degree of cooperativity decreases, I kind of expect this it's kind of an S-shaped curve to get kind of more and more dispersed out, and the higher the cooperativity, the more it looks like a discontinuity at that temperature. And so to first order, that's kind of how I would answer the question. But I think, discussing this maybe in a little more detail and looking at some of the details of this graph is pretty instructive for students.
Right, and I think one of the important issues here is that we are using concepts that are introduced in the context of a phase transition, a true first-order phase transition, like melting or evaporation. And we are using some of the ideas to discuss a different situation, that of changes in conformation at the molecular level. And cooperativity is another way to translate molecular interactions, how important are molecular interactions, and how this strength of molecular interactions or the range of molecular interactions translate into the shape of a curve like that. So that's what Jeff is saying, that if you increase the cooperativity, it should move in one direction, and if you decrease it, because it has to do with the degree of molecular interactions.
Right. And just like you would think of how does the cooperativity go, probably the most famous phase transition any student or anybody thinks of is like ice melting or a liquid forming a solid, right? You think of these things as having these, you can think of it as terms of molecular cooperativity, a nucleation and growth of a crystalline phase, for example. And this really bears out more in biological systems, oftentimes to look at this cooperativity versus what I would call the formal definition of phase transitions as being first order, second order, et cetera, as Ehrenfest type relationships, which is their discontinuity in state functions and higher order derivatives of those state functions, or order parameters in kind of a Landau.
Right. And probably, in this context, it's not entirely obvious how to use one of the most important properties that we have for phase transitions, that is that the chemical potential in phase A has to equal at equilibrium the chemical potential of phase B. So to write the chemical, it is possible to do it that way. But then the question is how you write the chemical potential for spaces like this, or if it is really equilibration, if you are truly describing an equilibrium situation, or whether this transition it's already, it's not completely, in some cases it can be an irreversible transition.
Right, yeah, exactly. Because in fact, most denaturization, the famous example you think of is frying an egg, right? Or something. Right. Well, that's clearly
which for Arizona is a very good example.
Because all you have to do is leave it outside.
Leave it outside, right? And then it will never come back to what it was.
Ever, no matter how much you cool it, no matter if you take it back, if you fry that egg, put it back in the refrigerator, it still doesn't
which
come
is
back.
A huge difference with, let's say, water ice phase transition.
No matter how many times you decide to melt your ice, if you put it back in the freezer, it refreezes.
Yes.
Exactly.
Yeah, because you can go around this equality to the situation where you have one of them being larger and the other being smaller.
And you can just switch that.
And you can switch this
and
condition.
most commonly use temperature to do it. But you can use pressure. You can use, you can use other.
So that's an important difference.
Very.
That this would be an irreversible.
Right. Well, and I like to,
in many cases.
But, but like you said, it's not just so clear cut in biology. Some things do have reversibility to them. Sometimes when they call chain melting in lipids, those are, reversible type reactions. Other things are not. When they go from DNA, they will call it apparent melting of DNA from its duplex to its singlet. And those can come back, or they can, get in situations where they can't. So, they often use what we think of when we teach very classic equilibrium-based chemical potential phase equilibria. Some of the biological systems are a lot more complicated than that, and some behave more ideally, more like a true. But it really is, in one regard, you would say kind of incorrect. And that's why at first order they'll say apparent melting, because it's not really a true, solid to liquid transition, which is how we would define it. But it's just kind of it has a lot of similarities. So it brings up a lot of the same physical pictures. And
I'm just thinking that this type of physics is also behind some types of cancer therapies, hyperthermia, because to kill a cell, you need to increase the temperature locally by only 2 or 4 degrees, and you kill the cell. And the reason is that these type of processes are extremely sensitive to that increase in temperature. And you might think that you need 20 or 30 degrees. No, it is enough.
And you're right. Even here at Arizona State, they have several people that use these, nanorod systems to, like you said, they do some type of specific binding and then try to come in and selectively heat those where it,
with a magnetic pulse.
Yeah, exactly.
But it's a magnetic hyperthermia. Exactly. That's what the one I had in mind.
So you're right. Like it's kind of amazing. These can be very sensitive to that. So hopefully this gave you, some general ideas of this type of behavior, and will lend to students being able to see, a discussion of this type of behavior in the book, and that it not only applies to this kind of fraction of unfolding, which they often use. I mean, this could be the fraction of duplex DNA. This could be the fraction of, chains in some lipid. I mean, they often will use this when they're looking at some type of cooperativity between two effects. But as you stated, like where you really want to get to is looking at, if it's equilibrium based, what its chemical potentials
exactly.
are between this.
Yeah. So biological systems are way more complicated than freezing water and
that's half the problems though, is that we always we start with these simple discussions of very simple molecules, and we make a huge quantum leap, to these really complicated systems without mentioning all these things in between. And I think it's often what confuses students the most, So thank you.
Yeah, thank you.